Hi, good morning, everyone. So we will start shortly. Wait for others to come in. All right, good morning. Good morning, all. So today, this week is week 13 already. So next week will be the last week for the lecture. And then after this, you will sit for the examination, which is the online. So the plan today is we want to finish chapter 5. We have another last part, which is the asynchronous serial communication, the UART, to be done. And we will continue to chapter 6, which is the timer and interrupt, the final chapter. So hopefully we can finish by today. And next week we will do the discussion and also the project presentation. I haven't created the link for project submission, so supposed to be this week. Yeah. So after this, I will create the link on Edmodo, so you can submit your mini project, or we call it assignment. Okay, so I think we can start now. So so last week we have learned on serial communication, where we have learned the two of the synchronous serial communication, which is the SPI, serial peripheral interface, and the integrated circuit, like to see. And today we will go to the last one, which is the universal asynchronous receiver transmitter, or in short, we call it UART. All right. So before that, let me summarize what we have done last week. Last week we have learned. We have been introduced to serial communication. And serial communication, you have two types. The first one is the synchronous, and the second one is asynchronous. Right. So last week we have looked at this, the SPI and the I2C. Okay. And for the asynchronous, where we want to learn today, is the UART, or universal asynchronous receiver transmitter. All right. So let's summarize what we have learned last week. The first one is the SPI. Okay. So in SPI, what you have learned is that when you want to do the communication using SPI protocol, so you need to have your microcontroller and set your microcontroller as a master or a slave. Can be either one. So the connection is like this. So you have your microcontroller and as a master, and you have slave. Okay, you can have many slaves. So in this case, let's use two slaves. And what you need to know is how we connect your microcontroller, the master, to the slave. For example, this is slave 1, this is slave 2. So you will need 2 wires, because the communication is we can say that it is simplex, which is one-way communication. All right, 1 wire, 1 direction. So you need to have 2 wires. First is for data line. We call it serial data line as DA, or that serial data out. Let's say that serial data out, and this one should be connected to the second one also, the same wire, and you should have the serial data in SDI, which is from the slave to the master. SDO is from the master to the slave. Okay, and you need another wire, which is the clock, to synchronize the transmission. All right, so the clock is used to help us to recognize the data. So 1 clock cycle represent 1 bit. All right, so that we can know that the data is this and that. All right, so this is SCLK, and you need to have another wire. This is for chip select, all right, or slave select, SS, all right, whatever you call it, CS. Okay, so this is how we connect the SPI protocol for serial communication. Okay, so now let's look at the advantage and disadvantage of the SPI link. Okay, so let's look at the good first, the pros. Okay, so what is that? So the first thing is it is simple, right? Simple. The communication is simple because this is the connection, and what is inside when we send the data, the inside is like this. For example, we want to send 0552 in hexadecimal. So the data will be something like this. So you need have a clock. All right, this is your clock, and this data is 8-bit. So you have 4, 5, 6, 7, 8. Okay, let's say we use mode 1, mode 0. So we will read our data at the every positive edge of the clock. All right, so the data will be 52 in binary is, so this clock, so we should have 5, so 0, 1, 0, 1, 0, 0, 1, 0. So the data will be like this. So the first one clock is 0, and the second clock is should be 1, and then 0, and then 1, and then 0, 0, 0, and then this one should be 1, and then 0. All right, so this is the data in the serial data out. So this is SCLK, the clock. All right, so the protocol is simple. All right, you have clock, and if the data is 8-bit, so you have 8 clock. You will have 8 clock pulse, 1, 2, 3, 4, 5, 6, 7, 8, and this is your data. and the first clock is 0. The second clock cycle is 1, 0, 1, 0, 0, 1, 0. All right. So we can say that the communication protocol is simple, and because it is simple, 8-bit data is one packet of data. All right. Means that when we send one package of data, the transmission is fast. So this is the advantage number 2 of the SPI. And now let's look at the cons, the disadvantage. What is that? So last week we have seen that if we increase the number of slaves, right? So you need another wire and another wire and another wire. So when you have more slave number, so the cost will also increase. Right. Number 2, we look at how the data is sent. So we send only the data, right? You can see this is the data 0, 1, 0, 1, 0, 0, 1, 0. There is no other information. So means that when the master send the data to the slave, there is no way for master to know whether the slave or the right slave is receiving the data or not. Means that there is no acknowledgement from the slave. So there is no acknowledgement. All right. So the slave not tell the master whether the data is received or not. The third one is that when you send the data, you also don't know at the receiving part and also at the receiver part, you don't know whether the data that you receive is correct or not. All right, because there is no error checking mechanism. There is no error check. All right, you send only data. All right, no other information. So there is no acknowledgement, there is no error check. So that is SPI communication. Now let's go to the next, the I2C. All right. So now the I2C, let's look at the connection first. So you will have the microcontroller, and let's say we have two slaves as well. Right, and the wire is now one wire for data, because the data line is two ways communication. This is a half duplex. All right, so this is serial data SDA, and you have another one is SCL, which is the clock. All right. So for I2C communication, so we need only two data. Okay. And these two data is you need to connect to the to the power line, right? You need a power line, and this one you need to connect to resistor, and the value of resistor can be somewhere between 2.2K to 4.7K, right? So this one is for the logic level when the data is not there, not on the line, or when IDLE, when idle. Okay, so let's say this one is slave 1, this one is slave 2, this one is microcontroller. Now we will see the difference is that we don't need this chip select, this wire, all right? And data line is only one now, all right? Because the sending and receiving, we use the same wire, all right? And the communication, we can call it, this is half duplex, right? Send using the same wire, receive using the same wire, okay? But the question is how the master recognize which slave is which, right? Which slave you want to communicate with. So the method is using the address, all right? So for example, this slave has a unique address of 02. This one is 04. And remember that the slave address must be an odd number, yeah? Sorry, even number. Okay. So how the data is sending, all right, from the master to the slave or from the slave to the master. Okay, again, we need to look at what is inside, what is on the line, yeah? Okay, so we have the clock line. Okay, so initially when no data, the state is high, and we also has the data as DA also high when there is no data. So when we initiate the sending, for example, we want to send to slave as send data 52 also to S1. So we will pull down the line as the A line to 0, means that this is the start. All right, the start bit. Okay, whenever the start, the system or the logic here going to down, immediately after this one going to down, this one will go down and the clock start to run. All right. So then we will send the first thing is the master will send the address and embed with the write or read signal. So for example, we want to perform the write signal, means that we want to send, right? So the signal UART should be equal to 0, and the address is 02. So the first 7 bit will be okay. This is first 7 bit with HD address, which is 0. This address 02, and followed by the write signal. Followed by the write signal. And then the slave will respond by sending the acknowledge signal, 1 bit acknowledged. So acknowledge will be logic 0 as well. So this is the acknowledge signal, followed by, and when the master receives the acknowledge signal, it will send the data, 8 bit. This is data to the slave, and then after the slave read the data, it will send the acknowledge signal and then stop. All right. So, and when you stop, the clock will go high, means that back to idle. All right. So this is how you communicate in I2C. So when you want to send a 1 bit, 1 byte data, how many bit you need to send? So we can calculate actually. All right. So let's see. You have address 7 bit plus you have read and write 1 bit, 1 bit. You have acknowledge 1 bit. This is acknowledged. You have 8 bit data here, and you have another 1 bit acknowledged. So for 1 byte data, how many bit you need to send? 8, 9, 10, 18. So 18 bit at least. Okay. So for now, we can compare what is the advantage of the I2C as compared to SPI. So let's look at this. So the pro of I2C is that, of course, we look at this when you add the number of slaves. If you have more slaves, right? You only need to expand the wire like this, right? So you no need to have extra wires like the SPI, because you don't have the chip select line. So it is always low cost as compared to SPI, right? The good thing is low cost as we compare to SPI. The second one is we have acknowledged. All right, we have acknowledged this one. Okay, so this acknowledge, the microcontroller will know whether the data is or whether the slave respond to the microcontroller or not, right? All right, so we have acknowledged to tell the microcontroller that you are talking with the right person, right device. Okay, so we have acknowledged. If there is no acknowledge, the acknowledge bit will be always 1. Yeah. If the acknowledge, if the slave respond to the master, the acknowledge will be 0. If no response, the acknowledge will be 1. Okay, so that will be the good of the I2C. And what about the bad? All right, nothing is perfect. Yeah. So first thing what we can see is that it is complicated, right? Okay, the protocol is quite complicated. So look at this. So you need to send the address, you need to have acknowledged. You need to have address, you need to have acknowledge, you need to have read write, and you have data and acknowledge and so on and so forth. You need to have the power line and so on. So it's more complicated as compared to SPI. And also, there is no error check just yet. Okay. All right. So that will be the SPI and I2C. Any questions so far? Okay. So if no question, we now also when we look at both SPI and I2C, we can see that both of the protocol, you need the clock. You need one extra line, clock line. You need clock. All right. And if the clock wire or the communication wire is long enough, sometimes the clock and the data may unsynchronize, may not synchronize anymore. All right. And also, when we look at here, okay, the frequency of the clock, all right, the frequency of the clock is 2 times as compared to the data, right? So you need, so this will limit the transmission speed. So you need 2 times clock frequency. Or you can say that frequency of the clock is 2 times bigger than the frequency of the data. All right. So this will limit your transmission speed. So this will limit the transmission speed. Okay. So for example, your communication line only allow for maximum 10 megahertz. All right. So this is for clock already. Means that the maximum speed for your data is 5 megahertz only. Right. So that is the disadvantage of the asynchronous serial communication. Now we will look at another kind of communication, serial communication, which is the asynchronous serial communication. Right. The good about this thing is first thing is you don't need clock. Okay, no need a clock. And the standard that we will use is the RS232 standard. And the protocol is named UART, Universal Asynchronous receiver, transmitter. Okay. And when we draw the communication between the microcontroller and peripheral or the slave, it will be something like this. Okay, so for example, this is our microcontroller, and this is the slave. And for this one communication line, you can have only one slave. Yeah, you cannot. If you need another slave, you need to have another line. So this one is the transmission from the microcontroller to the slave or receiver part. We call it transmit, TX. And at the receiving part, we call RX, receive. And this is TX for the slave, and then this is RX for the receiving part. So you have two lines. So means that this is simplex communication. So one is for sending and one is for receiving. So now we want to see data format, how the data is formatted on the line. Okay, so let's say, for example, we want to send this data 52 in hexadecimal. Okay, so 52 will be in binary will be 0101 0010, right? And for the UART, for the UART, the sending process will be LSB first. Means that LSB will go first. So when you look at SPI or I2C, okay, when you send the data, this is MSB. MSB. So MSB will go first. Also for SCI, I2C, the MSB will go first. MSB. But for UART, the bit that will go first is the LSB. So meaning that if you send this data through the UART communication protocol, so the data will be something like this: 0, 1, 0, 0. All right, reverse of order of this one. 1, 0, 1, 0. Okay, so this is the LSB. This is the MSB. Okay, and now because we don't have clock, so how the receiver and the transmitter format the data? How the receiver know that the data is 1 or 0? All right. So for example, again, if we send signal like this, all right, how the receiver know that this is 0, 1, 0, not 0, 0, 1, 1, 0, 0, and so on. All right. For the synchronous serial communication, we tell this receiver that this is 0, this is 1, 1 by using the clock. So one clock cycle represents one bit. But for asynchronous serial communication, we don't have clock. So how we tell the receiver that this is 0, 1, 0, not 0, 0, 1, 1, 0, 0. So the solution is that we use the duration of the bit. All right, the duration of one bit. So for example, we agree that for this communication, one bit, the duration of one bit is 1 microsecond. So for 1 microsecond, so the receiver know that, oh, this is 0. And another 1 microsecond, this is 1. Another 1 microsecond, this is 0. If we agree that we will use 0.5 microsecond for the duration of the bit, so meaning that this one 0.5 will be 0, another 0.5 will be 0, 0.5 will be 1, another 0.5 will be 1, 0, 0. All right. So that is how we talk to each other. All right, by using the duration of the bit, or in other words, we call it the speed of the transmission. Okay. So for example, when we say that our transmission speed is 1 kilo bit per second. All right. So meaning that we have duration per bit equal to 1 over 1 kilo. So this will be, okay, use your calculator. Should be 1 milli, right? Okay, so 1 milli, so it should be 1 millisecond. Okay, so meaning that 1 millisecond is 1 bit. All right, and if you are familiar with serial communication, so sometimes you can see that the transmission speed is 9600. We call it, the unit is baud, BAUD. All right. So for this communication speed, this is actually the duration per bit is 1 over 9600, which is approximately 104 microsecond. All right. Okay. So meaning that 1 bit is 104 microsecond for this communication speed. So let's go back to our data, which is 5.2. So 5.2 is 0.101.0010. Okay, and in communication and in UART, LSB will go first. So the data will looks like this: 0.1001010. Okay, so on the line, the TX line, okay, the ideal state is logic 1. All right. So how to tell the sender, how to tell the receiver that the data is starting here? So we will have another bit, extra bit, before the data. So this is the data. So we need another bit. We call it start bit. All right. And the start bit is logic 0 always. Yeah. So this is the start bit. And followed by your data. All right. So the next one will be, and this start bit, the duration will be 104 microsecond. The next 104 microsecond, 104 microsecond is this, the first bit, which is logic 0. And the next 104 microsecond is 1, which is this one, 0, 0, and then 1, 0, 1, 0, and then stop bit. Stop bit will be logic 1. So this is stop bit. You end with stop bit to tell the sender, the receiver that the data end here. So the stop bit will be logic 1 and the start bit will be logic 0. All right. So that is how the UART communication is done. Any question? Okay, so if no question, now we go back to this. Okay, when we look at SPI and I2C, we don't have this thing, right? Error check. Okay. In UART, here we don't have error check also. No error check. Error check. But actually, this communication protocol has error checking features, where before the stop bit, you can have the extra bit. We call it the parity bit, which is the error checking mechanism. All right. This is an option actually, where you can use, or if you want to use, you can set in your program that you don't want to use the parity. So if you want to use the parity, so there will be two type of parity. The first one we call it even parity, and the second one we call odd parity. All right. What is the difference and how the parity is used in the UART? So the parity is like this. When we decide to use even parity, so we need to decide whether the parity bit will be 0, 1 or 0. Okay. So how do we decide? Depend on the data. Okay. So for example, again, our data is 5.2 and on the line is 0. On the line is 0, 1, 0, 0, 1, 0, 1, 0, right? So when we agree to use even parity, we need to make sure that the total number 1 of our data plus the parity bit must be end up with even number. So for this case, the number of 1 in our data is how many? 3, right? So this is odd number. All right. So for this, we need to have another 1 as a parity bit, so that the total of number 1 in our data packet is 1, 2, 3, 4, which is even number. But if we decide to use odd parity, okay, when we decide to use odd parity, so we count how many ones in our data. 1, 2, 3. 3 is odd already, so the parity bit will be 0. All right. So that is how we use the parity. Okay. I repeat, yeah. Fatih asked why odd is 3. Okay. So I repeat again. The parity is the features for us to use as an error checking mechanism. So let's, for example, our data is this. We know that this is 5.2, all right? on the serial line. Okay, so if we decide to use even parity, means that our system use even parity. So means that the master use even parity, the slave also use even parity. So when we decide to use even parity, we need to make sure that the total of number 1 in our data plus the parity bit must be even number. So in this case, our data, we have 3 number 1. 1, 2, 3. 3 number 1. So to make it even parity, so we need to have another 1 as our parity bit. So that the total number 1 of our data packet is, the data plus the parity is 4, which is an even number. All right? You get that, Fatih? Okay. So now let's say we want to use odd parity, right? So again, we need to look at our data. So our data, we have 1, 2, 3, 3. So 3 is odd number already. This is odd number already. So if you put 1 here as a parity bit, you will have 4. 4 is even, which is wrong. All right. So because this is 3 already, yeah. So you need to have 0 as your parity bit so that the total number of 1 in your data plus the parity bit is an odd number. 1, 2, 3 plus 0, 3, which is odd. All right. Is it clear? Okay, good. Okay. All right. So now how this parity tell you whether the data you send is wrong or not wrong. Okay. So for example, you send this data through the line, right? So this is the TX line. So this is a long wire, and along this wire you have interference with other electronic devices, other wires, which is the electromagnetic wave. So this wave can be induced into the wire and may change. For example, you send number 1 like this, right? So maybe this noise will make your signal from 1 degraded to something like this, right? So this is not 1 anymore. So this is maybe 0. All right, recognized as 0 at your receiver end. Okay. So, for example, if we went, or maybe logic 0 here, because your wire induce another noise, make it this one got something like this. From 0 change to 1, from 1 change to 0. So when you send this, maybe because of the noise, all right, this from 1 change to 0. All right. So when you know that you use even parity for this case, for example, we use even parity, right? So even parity, again, go back again. Even parity last time, the original should be, this one is 1, this one is 1, right? Okay, so let's say when we send the data through the line, what happened at the receiver end is that this one, this number 1 change to 0. Okay, change to 0. So when the receiver receives this value, it will count 1, 2, 3. How many number 1 here? 1, 2, 3. You have 3. All right, and this is odd number. And we agree that we want to use even parity check, even parity. But we receive odd number, means that something went wrong. The receiver don't know which one is wrong, but definitely this is wrong, because we agree that we want to use the even parity and we receive odd. So something must be wrong. So the receiver may request for resend to the sender. All right. So that is the use of the parity. All right. Of course, if you have more, if you have more, for example, not this one, this also degraded to 0. All right. You will receive an even number also. Number 2 even, right? So this is even. Now the receiver don't know already which is wrong or right. So that is the drawback of a simple parity lah. So of course there are other error checking mechanism. You can learn this in serial communication, data communication course. But this will help you a lot in verifying the data that you receive. So most of the time, if only one bit is degraded, so we can know that we receive a wrong data. All right, so we can then request for resend from the transmitter. Okay, so that is the use of parity. So now we have error check feature in the serial communication already, right? Where the SPI and I2C don't have. Okay, any question before we go to the next? All right. So you can always refer back to the explanation on the video later on. I will upload on YouTube. Okay, so let's see how to implement the UART serial communication on the embed microcontroller. Right. So we need to go to our slide. Right. So we are here serial communication. Yeah. So this is the asynchronous serial communication and the UART. So this is how the data is formatted. So I explained this to you already. So this is the idle state where the logic is 1, and then this is the start bit 0, logic 0, and this is the first bit, which is the LSB. Okay, so see next, and until the last bit can be the parity bit. Okay, can be the parity bit, or if we don't want to use parity, so we don't have this bit. All right, and we have the this bit, and we have the stop bit, which is logic 1 before it go back to the idle state. All right, so meaning that if we transmit our data without the parity, okay, the data will be how many bit? So we have data 8 bit. For example, our data is 8 bit. So we have 8 bit data plus 1 start bit plus 1 stop bit. So the bit that we send is 10 bit. But if we have parity bit, so we have data 8 bit plus parity bit plus start bit plus stop bit. So you will have 11 bit if you use parity. Okay, so that is very straightforward. Now let's go to the this. So this is the program that we use to demonstrate the serial communication, the UART communication on the embed. So the function is serial, 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 and this is the object name. So can be any name, as always, can be any name. So you can name it. So this is P9, P10. So if we look at embed microcontroller, embed microcontroller. So let's look at this. Okay, so yeah, this is the serial line. So how many serial UART line that we can use in our microcontroller, the embed microcontroller? We have 1, 2, 3. So this is TX, this is RX. All right. So P9 is our transmit and P10 is our receive in this case. Okay, in this example. So let's go back to this. P9 and P10. And how do you set the speed? This is how we set the speed of our transmission. So our object name, our serial name is this, async port and dot baud, and the speed is this. All right. And for the default format in the embed is this. Format on the embed is 8-bit with no parity. So if you want to use parity, I will show you later. But on in the notes, we don't have. Later I will show you here how to have 7-bit. For example, you can have 7-bit system also. 7-bit with parity, for example, right? And how to send the data, very simple. This is how to send the data using the put C. Put C. So the put C here. Okay, put C your data, and here is your data. So let's look at example. I think better look at the example here. What is this? This is SPI, no. This is I2C, no. We want to look at serial. Do I have serial? Or maybe I name it UART. Oh, here. Okay, UART. Let's look at the simple example here. Can you see clearly I think the font is quite small and there is no way to make it big. Can you see my screen here? So this is the embed compiler. All right, the online compiler, where we want the compiler that we will use to write our program, to program our embed microcontroller. So this is a serial program, the very simple program to demonstrate the serial transmitting. So for example, we want to have our transmit data at this speed, 9600 baud, and if this is how we change the format of our transmission. So asynchronous port dot format, dot format, and this is the data size. If you want to use 8-bit, so use 8 here. If you want to use 7, so change to 7. So you can have 2, 7 or 8. All right. And this is parity odd. All right. And 1 here is your stop bit. All right. The stop bit, some of the system can be 2 stop bit, and some of the system use one stop bit, and by default use one stop bit. All right, so in this case we use one stop bit. Okay, so this is our data, and this is how we send the data. All right, put C. Okay, so with this we can look on the let's look the output on the oscilloscope. I have the oscilloscope. I don't want this. Let's see if this. The UART. Save the setting already. So let's see the setting for UART scope. Here. Okay. So these are the output of the TX line. The output on this TX line, and what is the data in this? So the data is let's go back to this A1. Yeah, A1. So A1 we use odd parity. Let's see. So A1, and okay. So let's have this. So I send A1. A is this, and 1 is this in binary. So meaning that when we send using UART, so we will have 1 0 0 0 0 1 0 1. Right, and we use odd parity. All right, we use odd parity. So the parity bit will be, okay, we need to count how many number 1 in our data. So we have 1, 2, 3. So we have 3 odd number already. So the parity will be 0. Right, the parity will be 0. So this should be the data that we can we will see on the TX line. So let's see, is it correct? Yes. This is the start bit. All right, so this is the start bit 0, and this is the first bit, bit 1 1 0 0 0 0 0 0 1 0 0 1 0 1, and this is the parity bit, and the last one will be the stop bit. So this is the stop bit. All right. Okay, so we can measure also the in this case the width of the let's measure the width of this the 1 bit. So all right, so this is 104 microsecond. Yeah, 104 microsecond, the speed of the transmission, or the duration of 1 bit. All right, so with that setting we have this. Okay, so that is how to use the serial communication in your embed microcontroller. So of course in your because you are at home now, you cannot access to the lab, you cannot use the microcontroller, and by using the embed simulator you cannot simulate this. So but for the exam you need to know how the theory work, how the data is formatted. So for example, let's after this look at the tutorial. All right, so you should expect the question something like the similar to the tutorial. Okay, so any question for the serial communication? the UART, the I2C, and the SPI. So this will be done already for the serial communication. Next is the exercise or the tutorial. So again, make sure that you try to do all the tutorial. So we have 9 questions. All right. Please do all the question. Try to do all the question so that you know how to answer and you can test your understanding also. Okay. So any question before we go to the next chapter? So far, so good. All right. Very quiet now. Okay, so if no question, let's look at the exercise a little bit. I don't want to answer the show you the answer yet. I want you to do the exercise first, and you can ask me. You have the question, right? So number 1 is very simple. Compare the advantages and disadvantages. I explained many times already. All right. What are the limitation of the number of devices? This one you can answer also. SPI link is running with 500 kilohertz clock. How long does it take for a single message containing 1 data byte to be transmitted? This is very interesting. Okay. If the clock is 500 kilohertz, okay, 500 kilohertz, how long does the data take? 1 byte, 1 data byte, 1 byte or 8 bit of data is transmitted through the line. Means that how long the receiver at the receiver part will receive the data. All right, 1 byte of data. Okay, SPI, and you can calculate. You can compare with I2C also, and also the UART, right? We can guess already that the longest time, the protocol that take the longest time is the should be the I2C, right? Because the data for I2C you need 18. One to send 1 byte of data you need 18 bit of data. Compared to SPI you need only 8 bit. 8 bit data, 8 bit. Yeah, you send 8 bit through the line. But for I2C, you send 8-bit data plus other information, address, acknowledge, read, write. So total you have 18 bit for 1 data package. All right. So that will take longer as compared to SPI. All right. But you need to calculate, right? Very easy to calculate. All right. You get the duration for 1 bit. The duration for 1 bit is easy. 1 over the clock, and you get already the duration, and you multiply with number of the bit that you need to transmit. Okay. So you can look at the question and try to answer the question, and if want to discuss, we will discuss maybe next week, right? Okay. Right. So if no question, so we will go to the next chapter.